Hello everybody. So we are going to answer the question that we answered that we were asking the previous video, which is that we got the velocity, the velocity profile, the average velocity for the condition that we mentioned, which is a laminar Newtonian fluid laminar flow for a Newtonian fluid in circular pipe. But we didn't get a formula for the pressure drop. And actually what we're going to use for the pressure drop is the equations that we formulated before for the velocity profile, and given the very important information that the dp by dx is constant for the case that we dealt with. So since dp by dx is constant, we can define dp by dx, which is the change of pressure with length, as delta p over delta x, which is pressure difference over length, because it's constant. So it doesn't matter how long the distance is, it's going to be the ratio is going to be constant all the way. So we can use this equation that the average velocity is negative r squared over 8 mu times dp by dx, but we are going to rearrange it to have dp by dx equals negative 8 mu u average over r squared. So this is the equation that we are going to use. And we are going to convert this r or use diameter instead of radius, so it's now multiplied by 4 up and down, so it's 32 mu lu average over d square. Keep in mind that in this equation we have delta p defined in a different way. Of course, before this, the equation is going to be valid for only the case that we derive this equation for, so it's not valid for any other condition or any other case. The second thing here is that the delta p is defined as p1 minus p2, and we don't have the negative sign here. And the reason we did this is because we don't want the pressure difference to be negative. We defined it this way, and this is what all the fluid mechanics textbooks and people who deal with fluid mechanics define it with. And it defines the amount of pressure that is lost due to the flow. So we don't put the losses as negative here, we're going to put it as positive, and delta p will always be the initial pressure minus the final pressure. Okay, so this is, from now on, this is how we are going to define this equation. This is the equation that we had. We combine this equation with this equation, so this is delta p over L, so multiplied by L, so this is L here, that makes the equation only for delta p. So it takes into account how much length the fluid is traveling through. Anyway, so this equation is a very useful equation, and it gives us very good idea about how the pressure drop is calculated. But we can get more out of this equation. So we know that this is the pressure drop equation, and if we rearrange this equation one more time, so we had it first as the or we go back to the original shape of the equation, but instead of having it as dp by dx, we put it as delta p over L. And this is the equation. If we want to calculate or get the formula for the volumetric flow rate, then we multiply this by the cross-sectional area, and of course it's only valid for the circular pipe, so the cross-sectional area is pi over 4 d squared. We can combine the d squared with the d squared, and we can write the equation this way now. So we have the equation written in terms of where the volumetric flow rate is calculated in terms of the pressure drop, which is a very good thing to know here, that usually the pressure drop is much easier to measure than the volumetric flow rate. I mean, if you have a simple YouTube manometer, you can easily find the pressure drop, while it's not the same for the volumetric flow rate. It requires special equipment to measure the volumetric flow rate. So this is one way we can calculate the volumetric flow rate in terms of the pressure drop, which is a very useful thing. The other useful thing is here actually, and this is a very important equation here. And by the way, this equation is called Poiseuille's law, or Poiseuille equation. But the what I want to focus here is this equation for the pressure drop. So there is something that we need to pay attention to, which is how the parameters affect the pressure drop. And usually when we calculate the pressure drop, we are doing the calculations for a specific volumetric flow rate. So if you design a pipeline, you know beforehand that this is the volumetric flow rate that you are handling, and based on this you do the calculation. So of course, as the volumetric flow rate increases, if all the parameters are the same, the pressure drop will be linearly increasing, and the same with length. And this is something we know from the beginning, because delta P is over L is constant. The same for the viscosity. As the viscosity increases, the pressure drop will increase linearly. The point I want to focus on here is this, that we have the pressure drop is inversely proportional to the fourth power of the diameter. And this is a very, very important piece of information here, that as you increase if the diameter is decreased by half, only by half, and if it's 1 inch, you made it half an inch for the same volumetric flow rate, for the same length, for the same viscosity, and for the same everything. If the diameter is decreased from 1 inch to half an inch, the pressure drop will increase 16 times. It's increased 16 times. It's 2 power 4. It's 16 times. If it's 1 atmosphere pressure drop, it will jump to 16 atmospheres of pressure drop, which is a huge increase in the pressure drop. Huge increase. So the pressure drop is highly sensitive to the diameter. So and this makes one very, very famous engineering task that we always see in all the pipeline designs, which is how can we choose the proper diameter. So we have two contradicting factors when we choose the diameter. First, we can think of the pressure drop. So we say we will pick a very big diameter, but the pipes with very big diameter will be very expensive, so we cannot increase the diameter a lot. And in the same time, it's more economical to decrease the diameter. I mean, for the pipe cost, it's going to be cheaper pipes that you'll buy that will have smaller diameter. But on the other hand, cheaper diameter or smaller diameters will lead to a huge or larger pressure drop, which means that you need to buy a larger pump that will overcome this pressure drop. Okay, so it's kind of an optimization problem. You go for higher diameter pipes, you'll need smaller pump and will need lower operating cost, but at the same time it will cost a lot for the pipes. If you go for smaller diameter pipes, it will cost less, but at the same time it will require larger pipes and larger operating cost. So this is a very, very famous optimization problem that we have in engineering. So the point, I'm not going to go through this now, maybe you can discuss it later, but the point I want to make here is it's very, very important to know that the diameter has a big effect on the pressure drop, and keep in mind that this is only for laminar flow. So for turbulent flow, it's even more effective. It's T to the power of 5. So if it's half from 1 inch to half inch in turbulent flow, it's not 16 times. It's going to be 32 times. Okay, so it's even. I mean 64 times, not 32 times. So this is a very, very important thing to keep in mind. So the Poiseuille's law states that for a specific flow rate, the pressure drop and thus the required pumping power is proportional to the length of the pipe, as we said, viscosity of the fluid, but it's inversely proportional to the fourth power of the radius or the diameter of the pipe. So this is a very, very important thing to keep in mind. So for now, we answered the question how we can calculate the pressure drop for laminar flow, and how we derive the equation for laminar flow or for the pressure drop. But as we said, it's only for this very, very specific case. Inshallah, next video we are going to go through if you go back, the second approach. So we are done with this approach now. We are going to go for the second approach, which is another equation that it's got experimentally, and that's the one that we are going to be using, inshallah, in the future for the calculations. So I'll stop here and we'll continue next time, inshallah. See you then.